Okay, so in this particular lecture, we continue our study of bifurcations. So, continued, and today we are going to see the example of a bead moving on a circular hoop. Of course, so we'll assume that there is friction. So what's the setup? The setup is I have a circular hoop and uh, I have a bead, a small ring over here, and the radius of the circular hoop is r, angle is phi, and I'll label this coordinate as rho. And I'll put the bead in some rotation, omega, and this is the rotation axis. So there are a lot of ways of doing this. Writing down the Lagrangian we'll just use Newton's laws. So let's apply Newton's laws, F equals to ma, to the system and see what happens. So it's convenient to go in the rotating reference frame. We'll go in the rotating reference frame. And as you know, if you go in the rotating reference frame, you will have a pseudo force acting. So I'll go in a reference frame where this hoop that was going by omega is at rest. So then what do I have? I have the bead. The forces on the bead are the gravity, mg, and what else do I have? I have a pseudo force, which is, if this distance was rho, if I am sitting on the circular hoop, then this bead is at rest with respect to me, and the bead circling around this circle of radius rho, I'll experience a centrifugal force outside radially over here. So geometrically rho is nothing but, this angle is phi. I'll erase this circle now. Yeah, so this angle is phi. Rho is nothing but r sine phi. That's what is geometrically. So let me try to apply Newton's laws in the tangential direction for the bead. So I have this guy r, so I'll just label the r as, doesn't matter, r. What is it equal to? So the phi dot is the acceleration in this particular direction, the rate of change of the angle phi, which is in the tangential direction. That is equivalent to some viscous force. I'm assuming the bead had friction, so this is a viscous force that will prevent the bead from going in the direction of increasing theta, so it has a negative sign. This was my force. This can be BR phi dot. And then I'll have the components of gravity, mg sine phi, that's going to act yeah, so this angle was phi geometrically. So the component of mg in this direction is nothing but mg sine phi with a negative sign. And then I'll have the component of this guy in this particular direction, which is going to give me m rho omega square, and the angle is cosine phi. So let's see if we have done it right. Yeah, I'm pretty sure we have done it correctly. And what is rho? Rho is nothing but r sine phi. So rho is nothing but r sine phi. So I plug in, I get this is what's happening. Yeah, so actually I should say this angle was phi if you calculate it, and this angle would be 90 minus phi. So why don't I just draw it again? These guys becoming a bit ugly. I have mg, this guy, this guy. This was the direction of m rho omega square. This angle was phi. This is how I got mg sine phi over here. This angle was 90 minus phi, and this angle is phi again. So that's how I got this component as m rho omega square cosine phi. And I plug the value of rho in, I get this equation. So this is the equation. Now I am going to make an assumption. So I just write down this equation again. Let's assume a scenario where we ignore this guy. We'll justify it under what conditions. So we are going to ignore this, but let's just assume that the motion is such that we ignore this term, which was saying the acceleration in the phi direction. We'll ignore this. So just follow me for now. Just follow me for now. Under what conditions we can neglect this? But let's see. I mean, the reason why we are going to do is that this was a nonlinear second order system. I want to remove the double derivative. I'm removing by, I will be making some physical arguments when we can neglect this, but just follow me. So then what does my equation say? This part was neglected. So then I have dr phi dot equals to mg sine phi, and in the bracket I have r omega square cosine phi by g minus 1. So this is just writing this term and this term like this. So now I have a first order system. I have only the first derivative. And then what do? I, as usual, try to find the fixed point. So certainly the fixed points occur at sine phi equals to 0. That can lead to the fixed point at 0 and the fixed point at pi. And of course, due to this guy, I'll have the fixed point as another set of fixed points, cos phi star equals to g over r omega square. These are also, when these conditions are met, we have another set of fixed points. So first look at the fixed points at 0 and pi. So what's going on? I have the fixed points at and when you do the stability alliance, so these are the fixed points. When the bead is here or over here, I get fixed points, and you can easily check intuitively when the bead is rotating. If it is here, it will be here, or it's here, it will be here. And intuitively it's obvious. You can also take the double derivative in the way we have done the stability analysis to see that phi star equals to pi is, as expected, unstable. The bead is going to probably trip down, and phi square equals to 0, the fixed point here, is stable. Usually this is the case. We can take the second derivative around that fixed point and check it. So what about the other set of fixed points? Now I have cosine phi star equals to g by omega r square. Now this has solutions. This has solutions if and only if g is less than r omega square. Only then cosine phi would be less than 1. So what can I do? I can define a dimensionless quantity gamma as r omega square by g. So this is a, you can check, this is the dimensions of acceleration. And let's see what's happening. I have cosine phi star is, in my parlance, 1 over gamma. So I can look at the intersection of these two curves. I have phi, and here is my curve cosine phi, and I have this guy, let's say 1 over gamma, and as this guy slides down, it intersects at 2 points. So over here 1 over gamma was greater than 1. Over here 1 over gamma is equals to 1, and then 1 over gamma becomes less than 1, and I get 2 fixed points. So this is terrific. I get a pair of fixed points, and of course they are symmetrical. They will be either side. And what's going on? So if you look at what happens to the stability of the fixed point at this guy. So I had a fixed point here, 2 fixed points here that are occurring, and this was phi star equals to 0. These are 2 symmetrical points. So you can also check if you plug in, so for example, mg sine phi r omega square cosine phi upon g minus 1, that was br phi dot, and we said that there was a fixed point here at this particular point. So why don't I take the double derivative? The double derivative is going to be mg cosine phi r omega square cosine phi upon g minus 1 plus I'll have mg sine phi, and I'll take the derivative of the thing in the parenthesis, sine phi upon g minus 1, and all this is evaluated at phi star equals to 0. This term is going to go off because of sine phi. I am remained with this guy. This guy comes out to be mg cosine phi r omega square cosine phi upon g minus 1. So if you look at it in the neighborhood of at phi star equals to 0, in the neighborhood of phi star equals to 0, if I have depending upon this term, the gamma, so I'll just put this as mg cosine phi. Remember, gamma was nothing but r omega square by g. So this is gamma cosine phi minus 1. So we need to check the stability of this guy at phi star equals to 0. And what's going on? As phi is for gamma, which is so I need from this plot hello? Yes, sir, office, please deliver in the office. Sorry about that, I got a call. Yeah. So when 1 over gamma is less than 1 or gamma is greater than 1, when gamma is greater than 1, what happens? This guy is going to be a positive quantity. So this point, when your f double dash becomes greater than 0, I have a condition for unstable fixed point. Any phi over here is just going to go away. So as soon as gamma becomes greater than 1, not only I get two fixed points which you can show are stable, my fixed point as phi star equals to 0 becomes unstable. So all in all, what sort of a bifurcation it is? We have studied this bifurcation. So this is indeed an example of a pitchfork bifurcation. I have symmetry. So in terms of the bifurcation diagram, I have this guy gamma, and gamma, as gamma grows greater than 1, I know that my fixed point at phi equals to 0 becomes unstable. We just showed that. And then I have two stable branches, two stable fixed points. Occur at gamma equals to 1. So this is a pitchfork bifurcation. So now come back to the parent question. When can we neglect this guy? So the standard approach is, just think about it. So I'll write down the equation again. I had the equation this guy, and we said that we have to justify how we neglected this guy. So there's a standard way of making these equations. So certainly when we are neglecting a term like this, we need to compare it. It has to be smaller as compared to other terms. So the easiest way to do is to make these equations into get these equations in their dimensionless form. So make this ODI into a dimensionless ODE, sorry, and then do dimensional analysis. Which is a very powerful way to analyze the system. So what do we do? So, what are the dimensions of phi dot? There's some radiance over time, so the dimension is something 1 over t. The dimensions of phi double dot are radiance over time and the derivative of that. So that is something like 1 over t square. T can be chosen later. So what we can do is that we can introduce a dimensionless time. The standard way, which is tau is t over t, or in other words, t, our time is nothing but tau, the dimensionless time, times the time scale in the problem. So then I have phi dot is nothing but d phi by dt, which is nothing but d phi by d tau by dt, which means I get this guy out, and then I have d phi by d tau. So that's the way I express my derivative in terms of the derivative with respect to the dimensionless time. The units of time gets extracted out. Similarly, phi dot dot can be written as 1 over t square d square phi by d tau square. You apply the chain rule and you get this. So in this particular parlance, substituting phi dot dot and phi dot into our parent equation over here, what do I get? I get m r square by t square phi dot dot. So now let me represent this phi as this guy. I am representing d square phi by d tau square as, let's say, phi dot dot. Phi dot dot equals to minus br upon t, similarly phi dot, plus mg sine phi gamma cosine phi minus 1. So what do I have? I have this guy. I can divide this equation by, let's say, mg. Then I have r over gt square phi dot dot equals to minus br over mgt phi dot plus sine phi gamma cosine phi minus 1. This is this. So now, if you look at it, I have basically, what is the dimension of this guy? This is length upon length t square. This is t square. Doesn't have any dimension. So I have reduced my original differential equation into a dimensionless form where all quantities are basically numbers. And now I can ask, when can I neglect something or the term involving the second derivative? Well, let's say this is order 1. So that means br over mgt is 1, which means t, my characteristic time scale, comes out to be br over mg. And I plug that guy into this guy again, I get r over gt square 1, and I plug the value of t from here, I'll get 1 over b square r over m square g is much less than 1, or in other words, m square g over b square r less than 1. So the condition I can neglect the second derivative is this guy, or in other words, m square is much less than b square r over g. So this represents inertia in the system, and this represents B was related to damping in the system. So in case of, you can say, overdamped thing where the the damping forces are much greater than the initial forces, I can convert this second order system into a first order thing and analyze this as a pitchfork bifurcation. So we learned two things today. We learned an example of pitchfork bifurcation arising in a dynamical system. And not only that, we also learned how to make an equation, reduce an equation into its dimensionless form by use of expressing it, making everything dimensionless. And then that helped us determining what are the relevant time scales or the order of magnitudes in the system. Well, thank you.